A space telescope just stared into the oldest light in the universe, and what it found sent scientists back to the drawing board. The James Webb Space Telescope launched in 2021 with a mirror the width of a school bus. It can catch light that traveled over 13 billion years to reach us. Real light. From galaxies that existed when the universe was barely a baby, and some of what it found shouldn't be there. Today, we're going to unpack all of it. The galaxy that shocked astronomers, the expansion problem nobody can solve, and why the phrase "behind the Big Bang" is both the most exciting and the most wrong thing you've ever heard. If you're enjoying this so far, subscribe. You won't want to miss where this goes. Prepare yourselves. We begin. Picture the most powerful eye ever built by human hands. It weighs about 14,000 pounds. Its mirror spans over 21 feet across, roughly the length of a large moving truck laid on its side. It took over 20 years to design, build, and test. Thousands of engineers across 14 countries worked on it. And on Christmas Day 2021, it launched into space on a rocket and began a journey that would shake the foundations of astronomy. The James Webb Space Telescope is the largest and most powerful space telescope ever sent into orbit. Hubble, which many of us grew up seeing photos from, had a mirror about 8 feet wide. Webb's mirror is nearly 3 times bigger. And size matters enormously here, because a bigger mirror catches more light. More light means seeing farther. Seeing farther means looking deeper into the past. Here's what's wild about Webb specifically. It doesn't see visible light the way your eyes do. It sees infrared light, which is essentially heat radiation, the kind of light that's invisible to you, but lets night vision cameras see in total darkness. Webb was engineered to catch that kind of light, because ancient galaxies billions of light years away have had their light stretched by the expansion of the universe. Visible light gets pulled and tugged over billions of years of travel until it arrives at Webb as infrared. Only an infrared telescope can pick it up. Think of it like sound. Imagine someone plays a note on a guitar. As they walk away from you, the sound waves stretch, the note drops lower in pitch. Light does the same thing across cosmic distances. Webb was built to hear that low note, and what it started hearing shocked astronomers. Within months of beginning its science mission, Webb was sending back images of galaxies that pushed the limits of what researchers thought was possible. Galaxies that looked too big, too bright, too chemically developed for how early they appeared in the universe's history. Scientists had models, they had predictions. Webb started testing every single one of them. One of the most important things to understand about this telescope is what it was actually built to do. Webb's official mission, stated by NASA, was to observe the first stars and galaxies that formed after the universe cooled enough to allow structure to exist. That happened hundreds of millions of years after the universe began expanding. Webb was designed to reach that era, to peak at cosmic dawn, the moment the first light switched on after an unimaginable stretch of darkness. Webb is a time machine in the most literal sense. Light travels at a fixed speed. When Webb catches light from a galaxy 13 billion light years away, that light left its source 13 billion years ago. Webb isn't seeing that galaxy as it is now, it's seeing it as it was then. Back near the beginning, every image Webb captures is a photograph of the ancient past. That's confirmed science. No debate, and the farther back Webb looks, the stranger things get. The telescope showed us something in the early universe that researchers are still trying to explain. A galaxy that existed when the universe was barely 300 million years old. A baby by cosmic standards. And it was doing things that babies aren't supposed to do. That galaxy is coming up soon. And it changes everything about how we think the early universe worked. You looked up at the night sky last night and saw lies. Every single star you saw was showing you its past. The closest star to our sun, Proxima Centauri, is about 4 light years away. The light hitting your eyes right now left that star 4 years ago. You're not seeing it as it is. You're seeing it as it was in the recent past. Go further. The Andromeda Galaxy, visible on a dark night as a faint smudge, sits about 2.5 million light years from Earth. The light reaching your eyes left Andromeda 2.5 million years ago, when early humans were just beginning to walk upright. Every time you look at Andromeda, you're watching a galaxy from the Stone Age. Telescopes don't just magnify, they time travel. This is confirmed physics, and it has a very simple explanation. Light moves at about 186,000 miles per second. That sounds impossibly fast. Across the room, light moves so quickly that the delay is completely meaningless. But across the universe, those tiny fractions of a second pile up into millions and billions of years. Distance becomes time. The farther something is, the older the light arriving from it. Webb sits nearly 1 million miles from Earth, far beyond the moon, in a region where its view is clean and unobstructed. From there, it collects light that has been traveling since before Earth existed, before our sun existed, before most of the stars you can see with your naked eye were born. When Webb captures an image of a very distant galaxy, researchers can measure how much that galaxy's light has been stretched during its journey. The technical word for this is redshift. The more stretched the light, the farther it traveled, the older it is, the earlier in the universe's history that galaxy existed. Picture a rubber band with dots painted on it. Stretch the rubber band and the dots move apart. The universe is doing this constantly, in every direction, at every point. Light crossing that stretching space gets pulled along with it. Short wavelengths of visible light get stretched into longer wavelengths of infrared light by the time they arrive at Webb after billions of years of travel. Webb is tuned specifically to catch those stretched waves. The galaxy called Jade's GS Zone 4-0, discovered by the James Webb Space Telescope and confirmed in 2024, has a redshift of 14.32. That is the highest confirmed redshift ever measured for a galaxy. And what that number means in plain terms is staggering. That light left its source less than 300 million years after the Big Bang. Webb caught light that has been traveling for over 13 billion years. That galaxy is confirmed to exist. The light is real, the measurement is solid, and the galaxy looked nothing like what scientists expected to find at that distance. The deeper Webb looks, the more the universe seems to be telling us that our models of how galaxies grow were built on incomplete information. We assumed the early universe was simple, chaotic, and dark for a long time before things got interesting. Webb is finding out the universe got interesting much faster than we thought. And the machine that makes all of this possible, it has to live in the most extreme conditions imaginable. Webb has to be one of the coldest objects in the entire solar system to do its job. The telescope operates at around minus 380 degrees Fahrenheit. To put that in perspective, the surface of Mars on a cold night gets down to about minus 195 degrees Fahrenheit. Webb runs at nearly twice that cold. We're talking about a temperature so extreme that very few things in nature ever reach it. The reason comes down to what Webb is hunting. Infrared light is heat radiation. Anything with a temperature above absolute zero, the coldest possible state of matter, gives off infrared light. Your body gives off infrared light right now. A warm cup of coffee gives off infrared light, and if Webb itself were warm, it would flood its own sensors with its own infrared glow, completely drowning out the faint, ancient signals from galaxies 13 billion light years away. So the telescope had to be made almost impossibly cold. Engineers designed a 5-layer sun shield, roughly the size of a tennis court, to block heat from the sun, Earth, and moon simultaneously. Each layer of the shield is thinner than a human hair, but stacked together, those 5 layers reduce the temperature from over 220 degrees Fahrenheit on the sun-facing side to the brutal cold on the telescope side. The shield blocks heat with an efficiency that is almost hard to believe. The most sensitive part of Webb's detector system, called the mid-infrared instrument, requires an extra cooling system on top of the sun shield. This instrument gets cooled down to around minus 447 degrees Fahrenheit. That is just a few degrees above absolute zero. The coldest naturally occurring temperature ever recorded in the observable universe is the cosmic microwave background radiation, which sits at about minus 455 degrees Fahrenheit. Webb's instrument operates close to that boundary. To build something that functions reliably at those temperatures, in the vacuum of space, 1 million miles from any repair crew, was considered one of the hardest engineering problems ever attempted. The mirror alone contains 18 hexagonal segments made from beryllium, a metal chosen because it holds its shape and reflects light well even at extreme cold. Each segment is coated in a microscopic layer of gold, because gold reflects infrared light better than almost any other material. When Webb launched, those 18 mirror segments were folded up like a flower bud to fit inside the rocket. Over the following month, they slowly unfolded and locked into position. Engineers then spent months aligning them to within a fraction of a wavelength of light. Every segment had to match up so precisely that the 18 pieces acted as a single perfect mirror. If even one step had gone wrong, the telescope would have been useless. There was no rescue plan. Webb launched knowing it was going to a place where no human hands could ever fix it. And yet, it worked. Webb reached its destination, unfolded perfectly, cooled down as planned, and began sending back images that changed how we see the universe. Every discovery it makes happens because a massive cold mirror, wrapped in a tennis court-sized sunshield, is sitting quietly in space, gathering ancient light. But where exactly did Webb park itself? And why there, of all places? Webb does not orbit Earth the way Hubble does. Hubble circles our planet every 97 minutes, roughly 340 miles above the surface. You could, in theory, send astronauts to fix it. And they did, multiple times. Webb's designers knew from the start that no such rescue mission would ever be possible, so they sent Webb somewhere entirely different. Webb orbits the Sun. Specifically, it sits at a location called the second Lagrange point, or L2. This is a position in space about 930,000 miles from Earth, always on the side of Earth facing away from the Sun. The Moon, by comparison, sits about 240,000 miles away. Webb is nearly 4 times farther out than the Moon. The Lagrange points are gravitational sweet spots. At L2, the combined gravitational pull of the Sun and Earth, combined with the orbital dynamics of the position, allows an object to orbit the Sun at exactly the same rate that Earth does. Webb stays locked roughly in line with Earth and the Sun, always hovering in Earth's shadow. This placement is not an accident. By sitting at L2 with Earth acting as a gravitational anchor, Webb can keep its massive sunshield permanently pointed toward the Sun, Earth, and Moon all at once. All 3 heat sources stay on one side, the telescope stays cold on the other. Move Webb even slightly out of alignment, and the whole thermal setup falls apart. Webb does make tiny adjustments periodically. Small thruster burns keep it in the correct orbital zone. Engineers calculated from the start that Webb carried enough propellant to maintain its position for over 10 years. Newer estimates suggest it may last 20 years or more, because the launch was so precise that very little fuel was needed to reach the right spot. 930,000 miles from Earth is a long way. A signal traveling at the speed of light takes about 5 seconds to reach Webb and 5 seconds to return. That might sound fast, but it means any command sent to the telescope has a 10-second delay before engineers even know if it was received. Every maneuver, every instrument adjustment, every data download has to be planned carefully. Webb sends its data back to Earth through a high-gain antenna, a large dish that points directly at our planet. The data travels at radio wave frequencies and gets picked up by ground stations around the world. The amount of data Webb generates is enormous. A single deep field image contains enough information to fill thousands of typical computer hard drives. Engineers at the Space Telescope Science Institute in Baltimore, Maryland, monitor Webb around the clock. The telescope is always operating, always collecting light, always building up an image of some distant corner of the universe. And what Webb has been staring at most intensely is the boundary of the observable universe, the furthest edge of what light can reach us from, the earliest moments that any telescope has ever touched. To understand what Webb found there, you first need to understand what actually happened at the beginning of everything. And the real story of the Big Bang is nothing like the explosion most people imagine. Most people picture an explosion, a single point in empty space, then a massive blast, fire and debris flying outward in all directions, like a bomb going off in a dark room. That mental image is wrong in almost every way. The Big Bang was the beginning of space itself. There was no empty room for it to happen inside. There was no single point it blasted out from. The explosion analogy falls apart completely the moment you understand what actually started expanding. About 13.8 billion years ago, everything that exists, all matter, all energy, all space, all time, was compressed into an unimaginably dense state. Scientists call this the initial singularity. And then it began to expand, rapidly, everywhere at once. Every point in space was expanding away from every other point simultaneously. There was no center. There is no edge where the debris landed. The universe didn't expand into empty space. The expansion created space. Every location in the universe was the location of the Big Bang, including the ground beneath you right now. Picture a raisin bread rising in an oven. The raisins are galaxies. As the bread expands, every raisin moves away from every other raisin. A raisin on the left edge of the bread sees all other raisins moving away from it. A raisin in the center sees the same thing. There's no special location. The dough itself is what's growing. NASA confirmed this. The Big Bang had no center you could point to on a map. It happened everywhere, and the expansion has never stopped. In the first tiny fraction of a second, the universe went through a phase of violent, rapid growth called inflation. Space expanded faster than the speed of light. That sounds impossible, but the speed of light only limits how fast objects move through space. Space itself has no such speed limit. During inflation, the universe grew from something smaller than an atom to something larger than a galaxy, in a span of time too short to describe with any everyday comparison. After that burst of inflation, the universe was an incredibly hot, dense soup of particles and energy, far too hot for atoms to form, far too hot for light to travel freely. Everything was a glowing, opaque fog. That fog lasted for about 380,000 years. During that time, no light could travel through space. The universe was completely opaque, like trying to see through the inside of a star. Any light that formed immediately collided with something else. The universe was its own prison for photons, the particles of light. And here is where a critical boundary appears, a boundary that no telescope, including Webb, has ever crossed. A wall between the visible and the invisible. Everything before that 380,000 year mark is hidden from direct observation, permanently. The fog blocked all the light from that era. What happened during inflation, what the universe looked like in its first moments, we cannot see with any camera or mirror ever built. Webb sees extraordinary things, but it sees, after the fog cleared, what came before remains one of the deepest mysteries in all of science. And the moment the fog finally lifted is even stranger than you'd expect. About 380,000 years after the Big Bang, something changed. The universe had been expanding and cooling since the very beginning. For almost 400,000 years, it was so hot that electrons and protons, the basic building blocks of atoms, were flying around separately. They couldn't stick together. Every time they tried, the intense heat ripped them apart again. Then the temperature finally dropped to around 5,000 degrees Fahrenheit, still far hotter than the surface of the sun, but cool enough for something that had never happened before in the history of the universe. Electrons and protons combined into hydrogen atoms for the first time. Atoms formed, and the moment atoms formed, the fog lifted. Before that moment, photons, particles of light, were constantly bouncing off free electrons. Light couldn't travel in a straight line for more than a short distance before hitting something. The universe was completely opaque, like the inside of a thundercloud, but in every direction, in every corner of existence. When electrons bonded to protons and became neutral atoms, they stopped scattering light. Photons suddenly had room to travel. The universe went from opaque to transparent in a cosmic instant. That first light, released when the fog cleared, is still traveling today. We can detect it. It has cooled over 13 billion years of expansion and now reaches us as a faint glow of microwave radiation from every direction in the sky. Scientists call it the cosmic microwave background. It is the oldest light in the observable universe, the afterglow of the moment the universe first became see-through. 3 telescopes mapped this ancient glow in detail. Kobe in the early 1990s, WMAP in the 2000s, and Planck, which finished its mission in 2013. These missions gave scientists a detailed picture of what the universe looked like at 380,000 years of age. Every tiny temperature variation in that ancient light corresponds to slight differences in density, the seeds that would later grow into galaxies and galaxy clusters. Webb cannot see behind that wall. No optical or infrared telescope can. The cosmic microwave background is the hard boundary of direct visual observation. Everything before it is hidden behind 380,000 years of opaque fog. Kobe, WMAP, and Planck detected that boundary radiation. Webb operates in a different wavelength range and targets galaxies that formed hundreds of millions of years later, well after the fog cleared. So any claim that Webb saw behind the Big Bang is scientifically impossible by definition. The phrase describes something that cannot happen with any telescope that works with light. The wall is absolute. The fog scattered and absorbed all electromagnetic radiation from that early era. Nothing visual from before 380,000 years has ever reached us. Webb's power is extraordinary, but it works within the laws of physics, and physics has drawn a hard line that separates what any camera can see from the very early universe. That distinction matters enormously when you start hearing viral claims about Webb breaking everything we know. Because the actual story of what Webb found, it's still shocking. And the most important part involves a headline that got almost everything wrong. Every few months, a headline appears that says Webb broke the Big Bang. Usually some version of Webb saw something before the beginning, or Webb disproved cosmology, or the title of this very video. These headlines spread fast. They get millions of views, and they are built on a misunderstanding of what Webb actually does. Let's be precise about this, because the reality is still fascinating. Webb cannot see before the Big Bang. The Big Bang did not leave a visible backdrop that a telescope could point at and photograph. The laws of physics forbid any electromagnetic telescope from reaching earlier than 380,000 years after the universe began expanding, because everything before that is hidden behind an opaque fog. Webb sees well after that fog cleared, targeting galaxies that formed hundreds of millions of years later. So the phrase behind the Big Bang confuses 3 completely different things. The first is seeing very early galaxies, which Webb actually does, and which is genuinely remarkable. The second is seeing the cosmic microwave background, the afterglow from when the fog cleared, which Kobe, WMAP, and Planck detected, and which Webb wasn't designed for. The third is seeing something from before the universe began expanding, which is impossible for any telescope using light, because no light from that era survived. These are 3 separate ideas. The headline mashes them into one, and in doing so, it replaces a genuinely dramatic real story with a false one. Here is what actually happened. Webb started finding galaxies in the very early universe. Some of them looked bigger, brighter, and more chemically complex than astronomers expected to find at that age. A few early candidates seemed so extreme that some researchers publicly wondered whether the standard model of cosmology needed serious revision. That speculation spread online. By the time it became a headline, some galaxies looked bigger than expected, had transformed into Webb proved the Big Bang is wrong. NASA's own scientists pushed back on this directly and clearly. The Big Bang is backed by 3 independent lines of evidence. Unexpected galaxies, even surprising ones, don't erase that framework. They challenge specific models of how galaxies form and grow. Those are different things. What Webb actually found is still enormously important. Some early galaxies do appear more developed than pre-launch expectations suggested. Researchers are actively reworking their models to explain why. That process of testing, finding surprises, and revising is exactly how science is supposed to work. And Webb found something else, something that the viral headlines mostly missed entirely. A separate measurement crisis that scientists are calling far more troubling than any single early galaxy. 2 different ways of measuring how fast the universe is expanding. 2 different answers. And Webb may have just confirmed the problem is real. Before galaxies, before stars, the universe went dark. After that initial fog cleared at 380,000 years, the universe entered a phase that astronomers call the Cosmic Dark Ages. It sounds like a dramatic name. The reality matches it. For hundreds of millions of years, the universe was filled with hydrogen gas and almost nothing else. No stars, no light, just cold, dark clouds of gas slowly pulled together by gravity. The Dark Ages ended when the first stars finally ignited. This moment is called Cosmic Dawn. It is one of the most important events in the entire history of the universe. Before Cosmic Dawn, there were no heavy elements, no complex chemistry, no possibility of planets or life. The universe was a dark ocean of hydrogen and helium. Then gravity squeezed enough gas into tight enough spaces that nuclear fusion began, and the first stars switched on. Those first stars were extraordinary. Scientists believe they were massive, maybe hundreds of times larger than our sun, burning intensely hot and living fast. They fused hydrogen into heavier elements, creating carbon, oxygen, nitrogen, the building blocks of everything complex. When they died, often in violent explosions called supernovae, they scattered those new elements into the surrounding gas. The universe was never the same after that. Webb was designed specifically to reach back to this era. Not the very beginning, not the fog, but the period starting a few 100 million years after the Big Bang, when the first structures were assembling, when the universe was transforming from a dark hydrogen ocean into the complex galaxy-filled cosmos we inhabit today. To reach that far, Webb uses its infrared sensitivity. Light from the first galaxies has been stretched by over 13 billion years of cosmic expansion. What started as ultraviolet light, the kind that causes sunburns, arrives at Webb as infrared. Only a telescope cold enough and sensitive enough to detect that stretched faint signal can study cosmic dawn. Webb was the first telescope powerful enough to actually do it. And the results were immediate. Within its first year of operation, Webb found galaxy candidates at distances that broke records regularly, candidates that appeared to exist only a few 100 million years after the Big Bang. Each one pushed the frontier of what we could observe. Each one forced astronomers to check their measurements more carefully. The most significant find came in 2024, a galaxy confirmed to have existed less than 300 million years after the Big Bang. A record, verified not just by infrared imaging but by a precise measurement of its redshift, using a technique called spectroscopy, which breaks light into its individual wavelengths and confirms distance with high accuracy. That galaxy's name is hard to say and harder to remember, but its properties are what matter. And those properties raise serious questions about how fast the early universe could build large, complex structures. Something was assembling galaxies faster than the models predicted. And the galaxy Webb confirmed is the most extreme example yet. In May 2024, astronomers announced a discovery that set a new record for how far back in time we have ever directly observed. A galaxy, confirmed, real, and existing less than 300 million years after the Big Bang. The galaxy carries a long technical label, Jade's GS Zone 4-0. Scientists on the Discovery team call it the galaxy when they're being casual. For our purposes, let's call it simply the record holder, because it holds the record for the most distant confirmed galaxy ever observed, with a redshift of 14.32. That number is the key. Redshift measures how much a galaxy's light has been stretched by the expansion of the universe. A higher number means more stretching. More stretching means more distance. More distance means the light left its source longer ago. At a redshift of 14.32, this galaxy's light left it when the universe was roughly 290 million years old. Our universe is about 13.8 billion years old today. That means we are looking at a galaxy from when the universe was barely 2% of its current age. Think about that like this. If the universe's entire history were compressed into 1 year, this galaxy existed on January 3rd. The discovery required 10 hours of observations with Webb's near-infrared spectrograph in January 2024. The spectrograph breaks light into its component wavelengths and creates what astronomers call a spectrum, a kind of light fingerprint that reveals what elements are present and how far away the object is. The redshift of 14.32 wasn't a guess or a rough estimate. It was a precise spectroscopic measurement, the gold standard in the field. And here's where the shock landed. The record holder is enormous for its age, over 1,600 light years across. To picture that, 1,600 light years is a span so large that light itself takes 16 centuries to cross it. And this galaxy achieved that size when the universe was less than 3% of its current age. The galaxy is also bright, strikingly bright, and it contains oxygen. Oxygen is a heavy element that only forms inside stars, after generations of stellar birth and death cycle through and enrich the surrounding gas. Detecting oxygen in a galaxy this young means stars had already lived entire lifetimes before this galaxy was even the size we see it at. Something came before the record holder, a whole earlier generation of stars, living and dying that we haven't directly observed yet. The Discovery team was genuinely surprised. They expected to find early galaxies. Webb was built to find early galaxies, but a galaxy this large, this bright, this chemically complex, this early in cosmic history, was outside what most of their models predicted. Scientists confirmed the find is real. The light is real, the redshift is real, the oxygen is real. And all of it points to one conclusion. Galaxies were growing faster in the early universe than researchers had assumed. But here's what many headlines got wrong about what this means. And here's where the story gets more complicated. When you build a model of the universe, you make assumptions. You take the known physics of gravity, gas dynamics, and radiation. You build computer simulations that run from the Big Bang forward and track how matter clumps together over time. And after decades of refinement, those models made clear predictions. Early galaxies should be small, they should be dim, they should be chemically simple, mostly hydrogen and helium, with very few heavy elements. The logic behind this was solid. Galaxies grow by pulling in gas and forming stars over long stretches of time. The older a galaxy is, the more time it has had to grow. An infant galaxy, existing less than 300 million years after the Big Bang, should look like an infant. Compact, simple, not yet developed. The record holder broke that picture. Over 1,600 light years across is large by any measure. For comparison, the Small Magellanic Cloud, a dwarf galaxy orbiting our own Milky Way, spans roughly 7,000 light years. The record holder is smaller than that. But the Small Magellanic Cloud has had over 10 billion years to grow. The record holder had less than 300 million years. The comparison isn't about size alone, it's about rate. How fast can a galaxy assemble mass and volume? The record holder did it at a speed the models said was too fast. The brightness compounds the problem. The record holder shines at roughly the luminosity that standard models reserve for galaxies many times its age. More luminosity means more stars. More stars in less time means star formation happened at a frantic pace. Stars were being born at a rate far exceeding anything the simulations predicted for that epoch. Then came the oxygen. Oxygen forms when massive stars fuse hydrogen into helium, then helium into heavier elements. When those stars die in supernovae, they scatter oxygen into the surrounding gas. For oxygen to be present in the record holder, an entire generation of stars had to live complete lives before this galaxy was even at the age we observe it. That implies star formation began even earlier than the record holder. There's a hidden generation. Stars that formed, burned, died, and enriched the universe with heavy elements, all before 300 million years had passed. And we haven't found those stars yet. Does this break the Big Bang? No. Scientists were direct about this. The Big Bang theory doesn't predict specific galaxy sizes or brightness at specific ages with perfect precision. What it describes is the overall expansion history of the universe, the formation of the cosmic microwave background, the abundance of light elements. All of those lines of evidence remain solid. What the record holder challenges is the specific models of galaxy formation, the sub-theories built on top of the Big Bang framework. Those models need refinement. Maybe early star formation was more efficient than assumed. Maybe early black holes played a different role. Maybe the physics of gas cooling in the early universe worked differently. Researchers are working on all of these possibilities right now. But before any of those explanations can be tested, you need to understand how we even know the record holder is that far away. And the answer involves a technique so clever, it borders on magic. Everything Webb sees is moving away from us. Every galaxy, in every direction, at every distance. The universe is expanding, and everything in it is carried along for the ride. That motion leaves a signature in light, and that signature is how astronomers measure distance across the universe. Here's the basic idea. Light travels as waves. Those waves have a length, the distance from one peak to the next. Different wavelengths of light appear as different colors. Short wavelengths are blue, long wavelengths are red. When a source of light moves away from you, the waves get stretched. The peaks spread apart, the wavelength gets longer, the light shifts toward the red end of the spectrum. This is called redshift. And every galaxy in the universe is redshifted, because every galaxy is receding from every other galaxy as space expands. The amount of redshift directly corresponds to distance. A small redshift means the galaxy is relatively nearby and its light hasn't been stretched much. A large redshift means the galaxy is very far away and its light has been stretched enormously during its long journey through expanding space. The record holder has a redshift of 14.32. For comparison, most galaxies visible to ordinary telescopes have redshifts well below 1. The Hubble Space Telescope struggled to see galaxies beyond a redshift of around 10. Webb operates in the infrared range, which allows it to detect the severely stretched light from galaxies with redshifts over 14. That is genuinely the frontier of the observable universe. When astronomers measure redshift precisely, they use spectroscopy. Webb's near-infrared spectrograph breaks incoming light into its component wavelengths, like a prism spreading sunlight into a rainbow, but with far greater precision. Every element in the universe absorbs and emits light at specific known wavelengths. Hydrogen absorbs light at one specific wavelength, in a lab on Earth. In a galaxy with a redshift of 14, that same hydrogen absorption appears at a wavelength over 15 times longer. The shift is enormous, and it's measurable with high accuracy. This is why spectroscopic confirmation matters so much. Early in Webb's mission, some galaxy candidates were identified using photometry, measuring how bright an object is in different wavelength bands. Photometric redshifts are estimates. They're useful for finding candidates, but can be wrong. Spectroscopic redshifts are precise. When a galaxy gets a spectroscopic confirmation, the distance measurement is solid. The record holder's redshift of 14.32 was spectroscopic, confirmed, precise. And that confirmation was only possible because Webb stared at that one galaxy for nearly 10 hours, collecting every photon of light it could gather, feeding it through the spectrograph, and building a detailed spectrum. The signal was faint, enormously faint. The galaxy's light had been traveling for over 13 billion years. Only the largest, coldest, most sensitive infrared telescope ever built could catch it. This technology, spectroscopy plus infrared sensitivity plus Webb's massive mirror, is what separates real confirmed discoveries from speculation. And in the months after Webb first began science operations, there was a period of intense speculation. Some galaxies looked even more extreme than the record holder. They seemed to challenge cosmology in an even bigger way. Then the spectroscopes checked the numbers, and several of those apparent record breakers turned out to be something else entirely. In the summer of 2022, Webb sent back its first deep images. Astronomers flooded the data. Within days, they were flagging galaxy candidates at extraordinary distances. Objects that, if their distances were correct, would exist impossibly early in the universe. Some candidates appeared to be more massive than anything that should exist at those distances. One group of objects seemed so extreme that a researcher posted publicly that they might be large enough to break the standard model of cosmology. That post spread fast. The phrase Webb broke the Big Bang was everywhere within weeks. The problem was that those early distance estimates were photometric. They were based on how bright the galaxies appeared across different wavelength bands, a useful but imprecise technique. Photometric redshifts can be off by significant amounts, especially for unusual objects. What looks like a galaxy at a redshift of 16 might turn out to be a galaxy at a redshift of 3 when spectroscopy gets involved. And when spectroscopy got involved, several of the most dramatic candidates were revised downward. One class of objects that caused significant excitement turned out to be galaxies at moderate distances, but with unusual dust properties that made them look much farther away than they were. Their light had been reddened by dust inside the galaxies themselves, mimicking the redshift that comes from cosmic distance. The telescopes weren't being fooled intentionally. The data was real. The interpretation was where the error crept in. This revision process was not a failure of science. It was science working correctly. In astronomy, especially at the frontier of cosmic distance, the process works like this. First, a wide survey identifies candidates based on rough measurements. Second, resources are allocated to follow up on the most promising or unusual candidates. Third, spectroscopic observations confirm or revise the initial estimates. Fourth, the refined data gets folded into models and compared to expectations. Steps 1 through 3 sometimes produce dramatic early headlines. Step 4 is where the real science happens, and the headlines go quiet. The record holder, the galaxy confirmed in 2024, made it all the way through that process. Spectroscopy confirmed its redshift. Its properties held up under scrutiny, the oxygen detection was verified, the size was confirmed. That's why scientists were so confident in the announcement. Every step of the confirmation process worked. Several other early candidates did not make it through. Their distances were revised. Their apparent sizes shrank. They were still interesting galaxies, just not the universe-breaking objects the early headlines described. What this episode taught the field is that Webb operates at the absolute limit of what is measurable. At that limit, initial measurements carry uncertainty. Extraordinary claims require the highest level of confirmation before they get treated as established facts. That standard exists to protect the integrity of the science. And by that rigorous standard, the genuine surprises Webb has confirmed are still extraordinary. Because some of those galaxies are real. The early universe was doing things faster than expected. The models need adjusting. And there's an entirely separate problem that Webb helped expose, one that has nothing to do with how big or bright early galaxies are, a problem that's been building for years and has now reached the level of a genuine crisis. The cycle you just heard about, quick announcement, viral spread, careful follow-up, quiet revision, is not a bug in astronomy. It's a feature. Science builds knowledge through a specific process that takes time. An exciting initial finding gets published or shared. Other researchers check the method. They look for errors. They run independent measurements. They compare the result to other data. If the finding survives all of that scrutiny, it gets incorporated into the established understanding of the field. If it doesn't survive, it gets revised or discarded. This process frustrates people who want clear answers fast. It's easy to look at a series of revised findings and conclude that scientists don't know anything. But the opposite is true. The willingness to revise is exactly what makes scientific knowledge reliable. Compare it to how a court case works. A witness makes a claim. The claim gets tested by cross-examination, physical evidence, other witnesses, and logical reasoning. If the claim holds up under all of that pressure, the court accepts it as established. If the claim falls apart under scrutiny, it gets discarded. Nobody criticizes the legal system for revising its conclusions when new evidence appears. That's the point of the process. Science operates the same way. A photometric redshift is a witness statement. A spectroscopic redshift is a piece of physical evidence backed by detailed analysis. When Webb's early wave of galaxy candidates went through that scrutiny, some survived and some didn't. The ones that survived became confirmed knowledge. For the discoveries that held up under rigorous examination, the implications are real and important. Galaxies in the early universe were forming faster than the standard models predicted. That specific prediction from specific models of galaxy formation needs revision. But revising a model of galaxy formation is different from overturning the Big Bang itself. The Big Bang describes the overall expansion history of the universe, the origin of the cosmic microwave background, and the abundance of light elements like hydrogen and helium. Those pillars are supported by decades of independent evidence from multiple instruments using completely different measurement methods. A few surprisingly large or bright early galaxies affect the galaxy formation models built on top of the Big Bang framework. They don't touch the framework itself. This is a crucial distinction that viral headlines consistently miss. Here's a useful way to picture it. The Big Bang theory is like the foundation of a house. Galaxy formation models are like the walls and rooms built on that foundation. Finding that some walls need to be repositioned doesn't mean the foundation is cracked. The foundation is still solid. The interior layout is getting revised. Researchers are genuinely excited about this. Finding an area where observations don't match predictions is exactly what drives progress. It means there's something new to understand. It means the early universe is more complex than assumed. And then there's the other problem, the one that Webb helped confirm. The one that doesn't involve early galaxies at all, but instead involves a disagreement about how fast the universe is expanding right now. That problem has a name, and it has been building since before Webb launched. The universe has been expanding since the Big Bang. Every point in space is moving away from every other point. Galaxies aren't flying through space. Space itself is growing, carrying the galaxies along with it. Picture a balloon with dots drawn on it. As you blow the balloon up, every dot moves away from every other dot. A dot on one side doesn't travel across the balloon's surface to reach the other side. The surface itself stretches. Every dot sees every other dot receding. None of them is the center. All of them experience the same thing. Now imagine measuring how fast the balloon is expanding. You could measure it from inside by watching how quickly nearby dots move apart. Or you could measure it from the beginning by looking at the pattern of dots when the balloon was tiny and calculating how fast it must have expanded to reach its current state. These two methods should give the same answer. If they don't, something is wrong with the balloon, or with the model of how balloons expand, or both. That's the problem astronomers are facing with the universe right now. The expansion rate of the universe is measured by a number called the Hubble constant. It describes how fast space is expanding for every unit of distance. A small Hubble constant means slow expansion. A larger one means faster expansion. For decades, measuring the Hubble constant was one of the central goals of observational astronomy. The Hubble Space Telescope was literally named for Edwin Hubble, the astronomer who first confirmed that the universe was expanding in the 1920s. Measuring the rate precisely became a decades-long scientific project. Two major methods developed over time. One looks at the early universe, specifically the cosmic microwave background, and calculates what the expansion rate should be based on conditions shortly after the Big Bang. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. A megaparsec is roughly 3 million light years. So for every 3 million light years of distance, the universe expands by about 67 kilometers per second. The other method measures the expansion directly in the nearby universe using carefully calibrated distance markers like certain types of stars and certain types of exploding stars. This method consistently gives a Hubble constant of about 74. 67 versus 74, those numbers look close. They're not. In cosmology, that gap is enormous. And the measurements on both sides have become more and more precise over the years, which means the gap should have closed. Instead, it stayed open. This disagreement is called the Hubble tension, and it has been one of the most debated problems in cosmology for over a decade. Some scientists argued the tension was caused by measurement errors, dust between galaxies, crowding effects in dense star fields, instrument calibration issues. If one side of the measurement was wrong, the tension would evaporate. Webb was built to help test exactly that. And when it did, the results were not what the tension skeptics hoped for. The Hubble tension kept scientists up at night for over a decade. If the discrepancy came from a measurement error, it was embarrassing but fixable. Someone made a mistake, the data gets corrected, and the universe makes sense again. But if the discrepancy was real, something in the standard model of cosmology was wrong. Something fundamental, something that nobody had figured out yet. Before Webb launched, one of the leading theories for the tension's cause was a problem with measuring Cepheid stars. Cepheid stars are a specific type of variable star that pulses in brightness on a regular cycle. The length of that cycle is directly tied to the star's true luminosity. By comparing the star's true brightness to how bright it looks from Earth, astronomers can calculate its exact distance. This makes Cepheid stars one of the most reliable distance tools in astronomy. The problem was that Cepheid measurements were done by the Hubble Space Telescope, and Hubble, despite being a remarkable instrument, has a smaller mirror than Webb and operates in visible light rather than infrared. In dense star fields where many stars overlap in the image, Hubble might blend multiple stars together and misidentify them as a single, unusually bright Cepheid. This blending effect is called crowding. If crowding was making Cepheids look brighter than they really are, the distance calculations would be wrong. The local expansion rate would be overestimated, and the tension might disappear once a better telescope checked the measurements. Webb was that better telescope. In early 2024, a team of researchers used both Webb and Hubble together to observe over 1,000 Cepheid stars across 5 different galaxies. These galaxies also hosted 8 Type Ia supernovae, a separate and independent distance marker used in the local expansion rate measurement. The study was the most comprehensive test of the Cepheid distance ladder ever attempted. Webb's infrared vision cut through dust and crowding far better than Hubble could. Its larger mirror resolved individual stars more cleanly in dense star fields. If crowding was artificially inflating the Hubble constant, Webb would catch it. The result came back in March 2024. Webb supported Hubble's earlier measurements. The Cepheid distances were consistent. The crowding effect was real but small, much too small to explain the full gap between 67 and 74. The local expansion rate remained stubbornly higher than the early universe prediction. NASA and the European Space Agency both announced the finding clearly. The Hubble tension persists. This is not a small measurement disagreement anymore. Both sides of the tension have now been tested with Webb's precision. Both sides hold up. The gap between them is real. And that means the standard model of cosmology, the framework that describes how the universe evolved from the Big Bang to today, is incomplete in some way that nobody has yet identified. That's a genuine crisis in cosmology, exciting to scientists, unsettling to models that took decades to build. And the key to understanding what might be missing starts with the stars astronomers use to measure those distances. Stars that pulse like cosmic heartbeats across billions of light years. Deep inside certain large aging stars, a layer of gas acts like a valve. When the star's core pushes energy outward, this layer absorbs the energy, traps it, builds up pressure, then releases a burst of light before contracting again. The cycle repeats. The star brightens, dims, brightens, dims in a steady rhythm. These are Cepheid variable stars, and they are one of the most powerful distance measurement tools ever discovered. The key property was found in 1908 by Henrietta Leavitt, an astronomer working at Harvard Observatory. She was analyzing photographs of a region called the Small Magellanic Cloud, a small galaxy close enough to the Milky Way that all the stars in it were at roughly the same distance. She noticed that Cepheids with longer pulsation cycles were consistently brighter than those with shorter cycles. The relationship was precise. It was a pattern that held up across dozens of stars. Her discovery meant that if you could measure how long a Cepheid takes to complete one pulse cycle, you could calculate its true luminosity. Then, by comparing that true luminosity to how bright it appears in your telescope, you could calculate its distance exactly. Distance equals the difference between how bright something looks and how bright it actually is. This technique is called the cosmic distance ladder. Cepheids are one of the most important rungs on that ladder. Edwin Hubble himself used Cepheids in the 1920s to prove that the Andromeda Galaxy was far outside the Milky Way, settling a debate that had consumed astronomy for years. Cepheids then became the anchor for measuring distances across hundreds of millions of light years. But Cepheids have limits. At very large distances, individual stars become hard to resolve from each other. This is where the crowding problem enters. In a distant galaxy, a field of stars packed closely together can look like a single bright object instead of many individual sources. Measuring Cepheids accurately at large distances requires resolving individual stars precisely. Hubble could do this up to a certain distance. Webb can do it farther and more accurately. For the 2024 study, the team didn't just recheck a handful of Cepheids, they observed over 1,000 of them across multiple galaxies, including galaxies that also hosted Type Ia supernovae, the next rung up on the distance ladder. Type Ia supernovae are bright enough to see across billions of light years, far beyond where individual Cepheids are visible. They work as distance markers because they all explode at roughly the same intrinsic brightness. If the Cepheid measurements were wrong due to crowding, the supernova distances would also be wrong, and the local expansion rate would be too high. Webb's ability to see through the crowding was supposed to fix that error. It didn't find a big error. The crowding effect existed but was small. The Cepheid distances were solid, and the local expansion rate remained at about 74. The tension held, and the implications of that are far larger than any single unexpected galaxy. Because if both sides of the expansion measurement are correct, then the universe is expanding faster today than the early universe conditions predict it should be. Something changed the expansion rate, and whatever it was is still missing from our models. Webb and Hubble worked together to confirm that the problem is real. The next step was to see just how real. 2 space telescopes pointing at the same galaxies. 2 generations of technology, one question that neither could answer alone. The 2024 Cepheid study required Webb's infrared precision for one critical reason. The galaxies being studied contain massive amounts of dust. Dust absorbs and scatters visible light, making stars look dimmer and redder than they actually are. Hubble, working primarily in visible wavelengths, sees this dust interference directly. Even careful corrections only go so far. Webb sees infrared. Infrared light passes through dust far more easily than visible light. A star that appears dimmed and reddened in Hubble's view appears at its true brightness through Webb's instruments. This dust penetration was the main reason the crowding hypothesis seemed so plausible before Webb. Maybe Hubble was seeing stars incorrectly because dust was blending and distorting their signals. Maybe the whole problem would disappear once an infrared telescope checked. The team ran their measurements carefully. They used Webb to observe Cepheid stars in 5 galaxies that also hosted recent Type I supernova explosions. These galaxies were chosen specifically because they bridged the 2 rungs of the distance ladder. Accurate Cepheid distances in these galaxies anchor the supernova brightness calibration. Accurate supernova brightnesses then extend the ladder to galaxies hundreds of millions of light years away, where the expansion rate can be measured directly. The results from Webb matched Hubble's Cepheid measurements. The dust corrections Hubble had been applying were accurate. The crowding effects were smaller than feared. The local expansion rate measurement, around 74 kilometers per second per megaparsec, was confirmed. On the other side of the tension, the measurement from the cosmic microwave background continues to give around 67. That measurement has been refined by Planck with extraordinary precision. The early universe expansion rate is one of the most tightly constrained numbers in all of cosmology. 2 methods, 2 answers, both confirmed by multiple independent measurements. The gap between them is real. NASA and the European Space Agency made this announcement jointly in March 2024. The language was direct. The Hubble tension persists. Webb confirmed Hubble's local measurements rather than resolving the discrepancy. The standard model of cosmology predicts a universe where these 2 numbers should agree. They don't. This is a meaningful crisis in modern physics, confirmed and announced by the agencies that operate the world's 2 most powerful space telescopes. The problem is real. The data is solid, and the explanation is currently unknown. Scientists have proposed several ideas for what might be causing it. Some involve adjustments to the behavior of dark energy, Some involve a brief burst of additional energy in the early universe that briefly sped up expansion. Some involve entirely new physics that nobody has detected yet. All of them remain theories. The exciting part is what comes next. Webb continues to observe. The distance ladder is being extended to farther and farther galaxies. Every new measurement either narrows the tension or confirms it stays open. Either outcome tells us something important about the universe. And there's something that might be causing all of this. Dark energy, the invisible force that controls the universe's expansion, is even stranger than the tension itself. Two numbers, a gap between them, and neither side budges. That sounds like a math problem. It's actually a crack in our understanding of the entire universe. Here's why the Hubble tension matters beyond the numbers themselves. The Standard Model of Cosmology is a framework built over decades using observations from dozens of instruments and thousands of researchers. It describes how the universe began, how it evolved, what it's made of, and where it's going. Every major prediction from that model has been tested and confirmed, from the cosmic microwave background to the abundance of hydrogen and helium to the large-scale structure of galaxy clusters. The Hubble constant is one of the fundamental parameters of that model. It sets the scale for everything else: how old the universe is, how large the observable universe is, how fast structures formed, how dark energy behaves over time. Get the Hubble constant wrong, and all of those calculations shift. The early universe measurement, around 67, comes from Planck's precise mapping of the cosmic microwave background. That measurement is deeply trusted. It's based on the physics of the early universe, which is well understood and backed by multiple independent observations. The local measurement, around 74, comes from Cepheids and supernovae in the nearby universe, now confirmed by Webb. This measurement reflects what the universe is actually doing right now in the present era. It's also deeply trusted. The gap between them means one of two things. Either one of the measurements contains a systematic error that nobody has identified yet, despite years of searching, or the universe's expansion rate genuinely changed in a way the standard model doesn't account for. If it's an error, it will eventually be found and corrected. If it's real, something happened between the early universe and today that accelerated the expansion beyond what the model predicts. And that something is currently unknown. This matters for everyone, not just cosmologists. Our understanding of the universe's ultimate fate depends on the expansion rate. If the universe expands faster than expected, it could affect predictions about how long galaxies will continue forming stars, how long before gravity stops holding cosmic structures together, and what the very end state of existence looks like billions of years from now. The expansion rate also connects directly to dark energy. Dark energy is the component of the universe that drives acceleration. If the Hubble tension is real, dark energy might behave differently than current models assume. It might not be constant, it might change over time, it might interact with matter in ways that haven't been detected yet. Changing the behavior of dark energy means changing the model of the universe's future. The tension isn't just about two numbers disagreeing, it's a signal that something is missing from our map of reality. And dark energy itself, even without the tension, is one of the strangest and most unsettling discoveries in the history of science. In 1998, two independent teams of astronomers made a discovery so strange they didn't trust their own results. They were measuring the distances and speeds of Type Ia supernovae, the exploding stars used as distance markers. They expected to find that the universe's expansion was slowing down over time. Gravity pulls matter together. The matter in the universe should be putting the brakes on expansion, decelerating it gradually. Both teams expected to measure that deceleration. Instead, they found the opposite. The expansion of the universe is speeding up. Distant supernovae were dimmer than they should be if the expansion was slowing. They were farther away than expected. The universe was not decelerating. Something was pushing space apart at an accelerating rate, and that something was invisible, undetected by any instrument. With no known source, scientists gave it a name: dark energy. The name is essentially a label for ignorance. We know it exists because of its effect on expansion. We have no direct detection of it. We cannot see it, sample it, or interact with it in any laboratory. It doesn't emit light, absorb light, or appear to interact with matter in any conventional way. Yet dark energy makes up about 68% of the total energy content of the universe. More than 2/3 of everything that exists in terms of energy is this invisible, unknown substance driving space apart faster and faster. Everything you can see, every star, every galaxy, every planet, every atom, makes up less than 5% of the universe's total content. Dark energy alone outweighs all of that by more than 13 to 1. The simplest version of dark energy is called the cosmological constant. Einstein originally introduced a similar concept when building his theory of general relativity, then abandoned it when Hubble showed the universe was expanding. After 1998, the cosmological constant came back as an explanation for acceleration. In this model, dark energy is a constant property of space itself. Every cubic inch of empty space has a tiny amount of dark energy built into it. As the universe expands and creates more space, the total amount of dark energy grows. The expansion feeds itself. This model fits the data reasonably well, but it has a problem. When physicists calculate from quantum mechanics what the energy density of empty space should be, the answer is enormously larger than what astronomers. The discrepancy is so extreme, it's been called the worst prediction in physics. Something is keeping dark energy much weaker than quantum mechanics says it should be. Nobody knows what. And now the Hubble tension is adding another layer of uncertainty. If dark energy has been constant throughout cosmic history, the two sides of the tension should agree. They don't. Some researchers think dark energy might be changing over time, growing stronger or weaker as the universe ages. If that's true, the cosmological constant model needs to be replaced. Webb is gathering data that could eventually reveal whether dark energy is constant or evolving. The answer will take years of observations and careful analysis. But some researchers aren't waiting for that data. They're already exploring a specific hypothesis, a burst of extra energy in the early universe that briefly pushed the expansion rate higher before fading away. That hypothesis has a name, and if it's correct, everything changes. The Hubble tension is a measurement problem. Two numbers that should agree don't. The question is why. One of the most actively debated explanations is called early dark energy. This is a theory. It hasn't been confirmed, but it's taken seriously by researchers, and it represents one of the most dramatic possible revisions to the standard model of cosmology. The idea goes like this. Dark energy, the force driving the current acceleration of the universe, may have a companion, a brief burst of additional energy that existed only in the very early universe, peaked around the time of atomic formation, roughly 380,000 years after the Big Bang, then faded away to almost nothing. This early dark energy would have slightly sped up the expansion rate during that brief window. Then it disappeared, leaving no direct trace in the current universe. Why does this help? Because the early universe measurement of the Hubble constant comes from the cosmic microwave background, which formed at exactly that 380,000 year mark. If early dark energy was present at that moment and briefly boosted expansion, the standard model's calculation based on the microwave background would slightly underestimate the true Hubble constant. The early universe measurement would come out lower than the real value. The gap between 67 and 74 would have a cause. This is a clever solution. It explains the tension without discarding the Big Bang, without throwing out the cosmic microwave background measurements, and without requiring completely new physics in the current universe. The extra ingredient existed early, faded, and left the modern universe looking almost exactly like standard cosmology predicts. Almost. Because early dark energy doesn't fix the tension perfectly. Detailed analysis shows it can reduce the gap, but struggles to close it entirely. And it introduces its own complications. Adding an early dark energy component changes predictions for the large-scale structure of the universe, specifically how galaxies and galaxy clusters are distributed across space. Those predictions then need to match observations of the actual cosmic web. Current data allows early dark energy as a possibility. It doesn't confirm it. Other explanations exist. Some involve modifications to general relativity, the theory of gravity that underpins cosmology. Some involve new types of particles that interacted with matter in the early universe. Some involve the possibility that the properties of dark energy change over time in ways that haven't been modeled yet. In December 2024, results from a large survey called the Dark Energy Spectroscopic Instrument suggested that dark energy might actually be evolving over cosmic time. That would be a significant finding if confirmed. It would mean the cosmological constant model is wrong, and dark energy needs a new description. Webb's ongoing observations feed directly into this debate. Every precise distance measurement, every well-confirmed galaxy redshift, every piece of data about the universe's structure at different epochs refines the constraints on these competing theories. The universe appears to be hiding something that shaped its history and controls its future, and it may have left a faint fingerprint in the oldest light we can detect. That oldest light is more remarkable than most people realize, and the telescopes that mapped it saw things that Webb, for all its power, cannot match. Webb gets most of the headlines, but 3 other missions hold the actual record for seeing furthest back in time. COBE, WMAP, Planck. These 3 satellite missions mapped the cosmic microwave background, the afterglow of the moment the universe first became transparent. That happened 380,000 years after the Big Bang. The light from that moment has been traveling ever since. Cooling, stretching, spreading in every direction. Today it reaches us as faint microwave radiation, coming equally from every point in the sky. Webb cannot see this light. Webb is an infrared telescope designed to detect galaxies that formed hundreds of millions of years after the fog cleared. The cosmic microwave background radiation exists at microwave wavelengths, far longer than infrared. Detecting it requires a completely different type of instrument, cooled to extreme temperatures and sensitive to completely different parts of the electromagnetic spectrum. COBE launched in 1989 and made the first precise map of the microwave background. Its measurements confirmed the Big Bang model and revealed tiny temperature variations in the ancient light. Those variations, fluctuations of about 1 part in 100,000, represented slight differences in density from place to place in the early universe. Denser regions would eventually collapse under gravity to form galaxies and galaxy clusters. COBE's discovery was so significant that the researchers behind it received the Nobel Prize in Physics in 2006. WMAP followed, launching in 2001, and producing a far more detailed map. WMAP measured those temperature variations with enough precision to determine the universe's age at about 13.7 billion years, the proportions of ordinary matter, dark matter, and dark energy, and the geometry of space itself, which turned out to be flat rather than curved. Planck launched in 2009 and produced the most detailed map of the microwave background ever made. Planck's data refined the universe's age to 13.8 billion years, pinned down the Hubble constant from the early universe side at around 67, and detected subtle polarization patterns in the ancient light that carry additional information about the very early universe. Planck's microwave background map remains the most precise picture of the universe at 380,000 years of age ever produced. All 3 missions looked further back in time than Webb can reach. Webb's earliest confirmed galaxy, the record holder, existed at 290 million years after the Big Bang. The microwave background missions mapped the universe at 380,000 years, nearly 800 times earlier. The microwave background is the oldest electromagnetic signal we can detect. Everything before it is hidden behind the fog wall of the early universe. And the picture these missions drew is extraordinary in detail. The slight temperature variations in the ancient light match the distribution of galaxies and clusters in the modern universe. The seeds visible in the microwave background grew over billions of years into the cosmic structures Webb now photographs at the frontier of the observable universe. These are 2 ends of the same story. One mission capturing the seeds, another capturing the trees they grew into. And together, they build a framework so well tested that even Webb's most surprising discoveries haven't cracked its foundation. Every few months, a discovery gets announced, and someone declares the Big Bang is over. Webb found unexpectedly large early galaxies. The Big Bang is broken. Webb confirmed the Hubble tension. The Big Bang is wrong. A distant galaxy contains oxygen it shouldn't have yet. The Big Bang has failed. These claims are exciting to read. They are not supported by the evidence. The Big Bang model rests on 3 independent and well-tested pillars. Each one would have to collapse individually for the model to fail. So far, none of them has. The first pillar is the expansion of the universe itself. Every galaxy beyond our local group is moving away from us. The further away it is, the faster it recedes. This was confirmed by Edwin Hubble in the 1920s and has been measured more precisely with every generation of telescope since. Webb itself confirms this expansion every time it measures a galaxy's redshift. The universe is expanding. That is beyond dispute. The second pillar is the cosmic microwave background. If the universe began in a hot, dense state and expanded and cooled, there should be a faint glow of radiation left over from when the universe first became transparent. That glow should come equally from every direction in the sky, with tiny temperature variations matching the density fluctuations that seeded galaxy formation. Kobe, WMAP, and Planck found exactly that, exactly where and how the Big Bang model predicted. The third pillar is the abundance of light elements. In the first 3 minutes after the Big Bang, when the universe was hot enough for nuclear fusion, protons and neutrons fused into hydrogen and helium nuclei in specific ratios. About 75% hydrogen and 25% helium by mass, with trace amounts of lithium and deuterium. When astronomers measure the composition of ancient gas clouds in the universe, before stars had time to make heavier elements, those ratios match the Big Bang prediction extremely well. 3 pillars, each tested independently, each confirming the same framework. Unexpected early galaxies challenge galaxy formation models. The theories about how fast structures assembled after the Big Bang, those models are built on top of the Big Bang framework, but they're not the framework itself. Finding that galaxies grew faster than expected means the galaxy formation models need adjustment. It means the physics of star formation in the early universe is more efficient or different than assumed. The Hubble tension challenges the completeness of the standard cosmological model, specifically the dark energy component. If the expansion rate genuinely disagrees with the early universe prediction, something is missing from the model. That missing piece is a serious problem. But it's a problem with one parameter of the model, not the foundation. Revising a model is how science advances. The history of physics is full of theories that were refined, extended, and improved as better data arrived. Newton's gravity worked well for 2 centuries until Einstein showed it needed refinement at extreme speeds and masses. Einstein's equations still underlie modern cosmology. Refinement didn't erase Newton, it extended him. The Big Bang model will almost certainly need refinements. Webb is helping identify where those refinements are needed. That's exactly what a scientific instrument should do. And what Webb has revealed about how galaxies actually formed in the early universe is one of the most dramatic stories in modern astronomy. Before the first galaxy existed, the universe was a dark, cold ocean of hydrogen gas. The Dark Ages lasted hundreds of millions of years. Gravity was working the whole time, slowly pulling clumps of gas together, building density in some regions, and emptying out others. The process was gradual at first, then it accelerated. When a region of gas became dense enough, gravity won decisively. The gas collapsed inward. As it fell, it compressed. Compression raised the temperature. Eventually, the core reached temperatures of millions of degrees, hot enough for nuclear fusion to ignite. A star was born. The first stars were almost certainly enormous. Estimates suggest they may have been hundreds of times more massive than our sun, burning through their fuel at a rate so fast that their entire lives lasted only a few million years. Our sun will live about 10 billion years. Some of these first stars may have burned out in less than 3 million. When they died, they didn't fade quietly. A star hundreds of times the mass of our sun ends its life in a collapse so violent it releases more energy in seconds than our sun will in its entire lifetime. These explosions, called supernovae and hypernovae, scattered heavy elements into the surrounding gas: carbon, oxygen, silicon. Iron elements that had never existed anywhere in the universe before. Those scattered elements changed everything. Gas enriched with heavy elements cools differently than pure hydrogen. Enriched gas can form dust grains. Dust grains allow gas to cool faster. Faster cooling means denser clumps. Denser clumps means more stars form more quickly. The first generation of massive stars triggered a cascade that accelerated star formation across the early universe. Meanwhile, small galaxies were assembling around the densest knots of dark matter. Dark matter, the invisible material that makes up about 27% of the universe's total content, clumped first because it doesn't interact with radiation the way normal matter does. It collapsed into halos under gravity. Normal matter followed, falling into those halos and forming stars at their centers. The first galaxies were small, irregular, explosive with star formation. They collided with neighboring proto-galaxies and merged, building larger structures. Those merged into larger ones. Over billions of years, through countless collisions and mergers, the modern Milky Way assembled from thousands of smaller predecessors. Webb sees this process frozen in time across different epochs. Each distant galaxy Webb images existed at a specific moment in cosmic history. By comparing galaxies at different distances, astronomers can watch galaxy formation unfold across time, like flipping through a photo album of the universe aging. What Webb showed is that some steps in this process happened faster than the album predicted. Some early galaxies assembled more mass, formed more stars, and built more chemical complexity in less time than the models expected. The cascade started earlier and ran faster than assumed. That means something in the physics of the early universe was more efficient than researchers thought. And one candidate for that efficiency boost is hiding at the centers of those early galaxies, doing something that should take far longer than it apparently did. The record holder galaxy exists less than 300 million years after the Big Bang. Inside it, astronomers detected oxygen. Oxygen doesn't come from the Big Bang. The Big Bang produced hydrogen, helium, and tiny amounts of lithium. Every oxygen atom in existence was forged inside a star. For oxygen to exist inside the record holder, a previous generation of stars had to live complete lives, going from birth to death inside a galaxy that existed before the record holder itself. That earlier generation is called population 3 stars by astronomers, the very first stars, the ones that ignited during cosmic dawn. Nobody has directly detected them yet. But the oxygen in the record holder is indirect proof that they existed and that they died before 290 million years had passed. This has a specific implication. The star formation rate in the very early universe, in those first 200 million years before the record holder, must have been high enough and fast enough to produce stars that enriched the surrounding gas before the record holder's own stars formed. That's a compressed timeline with very little room for slow or inefficient processes. Confirmed data from multiple Webb observations shows a pattern. Galaxies in the first few 100 million years are forming stars at rates far higher than expected. Star formation rate is measured in solar masses per year, basically how many sun-sized stars the galaxy creates every year. Some of these early galaxies were building the equivalent of hundreds of stars per year. The Milky Way today creates roughly 1 to 3 stars per year. The early universe was a stellar factory running at full capacity. One proposed explanation is that early gas was denser and more turbulent than later generations of gas clouds. Denser gas collapses faster. Turbulence creates many collapse points simultaneously. A single large gas cloud might fragment into dozens of star-forming cores at once, rather than forming one star at a time. If the first gas clouds were more prone to this kind of fragmentation, the early star formation rate would be naturally higher. Another explanation involves the lack of heavy elements themselves. Pure hydrogen and helium gas, without the dust and heavy elements that form later, behaves differently under gravity. It doesn't cool as efficiently through certain processes, but it can still collapse, and when it does, the resulting stars tend to be more massive. More massive stars live faster and die sooner, replenishing the surrounding gas with heavy elements quickly. The cycle accelerates itself. A third explanation involves feedback from supermassive black holes. If early black holes were already large, their energy output could have compressed surrounding gas clouds, triggering rapid starbursts. This would create a feedback loop where black hole growth and star formation drive each other in the early universe. That last idea connects to one of the deepest puzzles Webb has uncovered. Because the supermassive black holes themselves, sitting at the centers of those early galaxies, are also there far too early, and their existence is arguably more difficult to explain than the galaxies around them. At the center of nearly every large galaxy sits a supermassive black hole. The Milky Way has one. It's called Sagittarius A star, and it contains the mass of about 4 million suns packed into a region smaller than our solar system. Black holes grow by consuming gas, dust, and stars that fall into them. A black hole swallows matter, and that matter adds to its mass. This process has a speed limit. As matter falls toward a black hole, it heats up and radiates energy outward. That outward radiation pushes against incoming matter, limiting how fast the black hole can feed. This maximum feeding rate is called the Eddington limit. If a black hole feeds at the Eddington limit continuously, growing as fast as physics allows, it still takes an enormous amount of time to reach a mass of billions of suns. The problem is that Webb keeps finding supermassive black holes in the very early universe. Black holes already containing hundreds of millions or even billions of solar masses, present less than 1 billion years after the Big Bang. By standard growth models, they shouldn't be anywhere near that size yet. One confirmed example, astronomers using Webb detected an active supermassive black hole in a galaxy, existing only about 400 million years after the Big Bang. That black hole was already tens of millions of solar masses in size. Even starting from a stellar mass black hole formed by a dying star and feeding continuously at the maximum possible rate, the math doesn't add up to produce that mass in that time frame. Something made them big much faster than standard growth allows. Several theories are under active investigation. One involves direct collapse black holes. Instead of forming from stellar remnants and growing slowly, some black holes in the early universe may have formed directly from the collapse of massive gas clouds, skipping the stellar phase entirely. A collapsing gas cloud of 100,000 solar masses would form a black hole of 100,000 solar masses immediately, providing a much larger starting point. Another theory suggests early black holes briefly exceeded the Eddington limit, feeding at rates beyond what the standard model permits. This super Eddington accretion, if it occurred in dense early environments, could explain rapid growth without requiring new physics from scratch. Whether either of these mechanisms actually operated in the early universe remains unconfirmed. Webb is gathering data on early active black holes at a pace that should provide clearer answers within the next few years. What's confirmed is that supermassive black holes were present and already massive very early in cosmic history. That fact, standing alongside the unexpectedly large and bright early galaxies, the detected oxygen, and the star formation rates, paints a picture of the early universe as a far more active and rapidly evolving place than researchers assumed. And one detail inside the record holder galaxy makes all of this even stranger. A detail that seems small but implies an entire hidden history that nobody has yet observed directly. Dust sounds ordinary. In everyday life, it's something you wipe off a shelf. In the early universe, dust is a profound mystery, because dust, in the astronomical sense, is made of heavy elements. Carbon grains, silicon grains, ice coatings. These are materials that can only be produced inside stars, after nuclear fusion forges them from lighter elements and then scattered into space when those stars die. No dust exists before stars. Dust requires stars to live and die first. Generations of stellar life and death are baked into every dust grain. When astronomers analyzing the record holder galaxy detected dust in its spectrum, they immediately understood what that meant. This galaxy existing less than 300 million years after the Big Bang, contained the remnants of stars that had already lived entire lives before the record holder's own light reached Webb. An entire hidden generation, stars that formed, burned, scattered their material, and disappeared, all within a time frame smaller than many people assumed the early universe even allowed for significant stellar activity. Finding dust is direct evidence of prior stellar generations. It's like walking into a room and seeing ash in a fireplace. You didn't see the fire, but you know there was one. Researchers have proposed that the earliest massive stars lived and died fast enough to enrich their surrounding gas with dust before 300 million years elapsed. Massive stars burn through hydrogen in millions of years rather than billions. A universe that formed massive stars early and rapidly could produce dust on a compressed timeline. Some dust production models suggest supernovae from those first massive stars could generate dust quickly enough to explain what Webb sees. The exact mechanism by which that much dust formed that quickly remains an open question. Laboratory measurements of dust production in supernovae suggest individual explosions don't make enormous amounts of dust. But if early supernovae were frequent enough, the cumulative output could build up. What makes this specific detail important is what it implies about the hidden history before the record holder. There's a chapter of the universe's story that nobody has directly read yet. A time before 300 million years after the Big Bang, when stars formed, lived, and enriched the universe with heavy elements. Webb found the footnotes. The main text is still missing. Those missing stars may be findable. Webb and future instruments are searching for galaxies at even higher redshifts, pushing the boundary further back toward cosmic dawn. Every new confirmed galaxy at an earlier epoch adds a sentence to that hidden chapter, but there's a wall, a hard limit. Beyond a certain distance, the universe is opaque again, not with the fog of neutral hydrogen, but with the reionization frontier, the boundary where the first stars were actively ionizing the surrounding gas, making it difficult to observe through. And beyond even that frontier lies the region no optical or infrared telescope can ever reach, the true wall, the one even Webb cannot cross. Webb is the most powerful infrared telescope ever built. It can detect light that left its source over 13 billion years ago. Its confirmed discoveries reach to within 290 million years of the Big Bang. And there is still a hard boundary that Webb cannot cross. The first problem is practical. Even Webb's extraordinary sensitivity has limits. Galaxies at the very highest redshifts are incredibly faint. The light has been traveling for over 13 billion years. Most of it never reaches Webb at all. Collecting enough signal for a precise measurement requires hours of observation time for a single object. Webb has finite observing hours across its mission lifetime. Not every candidate can receive 10 hours of spectrograph time. The second problem is fundamental. Between roughly 400 million and 1 billion years after the Big Bang, the universe went through a phase called reionization. During the cosmic dark ages, after the initial fog cleared at 380,000 years, the universe filled with neutral hydrogen gas. Neutral hydrogen absorbs specific wavelengths of ultraviolet light very efficiently. For a period, this neutral gas acted as a partial fog, making the universe difficult to see through for certain wavelengths. The first stars and galaxies produced intense ultraviolet radiation. Over hundreds of millions of years, that radiation ionized the surrounding hydrogen, stripping electrons away from the atoms and making the gas transparent again. By about 1 billion years after the Big Bang, reionization was essentially complete. During the reionization era, observations become increasingly difficult. The neutral hydrogen in between galaxies absorbs parts of the light spectrum that Webb would otherwise use for measurements. This creates gaps in the data. Spectroscopic measurements become harder to interpret. Some distance ranges are partially obscured. The third problem is the fundamental limit described earlier, the cosmic microwave background wall at 380,000 years. Before that moment, the universe was opaque to all electromagnetic radiation. No photon from that era has reached us intact. No telescope that works with light, from radio waves to gamma rays, can see directly into that period, What lies beyond that wall is genuinely unknown from direct observation. The physics of inflation, the extreme conditions in the first fractions of a second, the nature of the initial singularity, these are questions that electromagnetic telescopes cannot answer. The wall is absolute. Scientists know that the universe has more history before 380,000 years than it has after, in terms of physical processes and extreme conditions. The first 3 minutes of nuclear fusion, the first second of particle-antiparticle creation and annihilation, the first tiny fraction of a second when inflation occurred. All of it hidden. But hidden behind light doesn't mean hidden from everything. There are signals that don't travel as light. Signals that could, in principle, pass through the fog. Signals from the deepest past that a completely different kind of detector might someday catch. Those detectors are being built right now, and what they might reveal could be the most dramatic chapter in the history of astronomy. Light is not the only messenger the universe sends us. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. These are ripples in the fabric of space-time itself, generated when massive objects accelerate. Two black holes colliding send out waves of warped space that travel at the speed of light and pass through matter without being absorbed. Gravitational waves don't interact with the cosmic microwave background fog. They don't scatter off charged particles. The early universe was completely transparent to them. In principle, gravitational waves generated during inflation or during the very first moments of the universe would still be traveling today, carrying information from before the electromagnetic war. Detecting primordial gravitational waves from inflation is one of the most ambitious goals in modern physics. Current detectors like LIGO operate at frequencies suited to detecting waves from stellar mass black holes and neutron stars. They're not designed to detect the background hum of gravitational waves from inflation. Future space-based detectors, including the Laser Interferometer Space Antenna, planned by the European Space Agency, are designed to detect lower frequency gravitational waves from much larger and more massive events. These instruments would operate over a baseline millions of miles long, far too large to build on Earth. The sensitivity required to detect primordial gravitational waves from the very early universe would require even more advanced technology beyond what's currently under construction. If inflation produced a strong enough background of gravitational waves, future detectors might eventually pick up that signal. Detecting it would provide direct evidence of what happened during inflation, the period of rapid expansion in the universe's first fraction of a second. That would be closer to seeing the Big Bang than anything ever achieved. There's another possible messenger, neutrinos. These are particles so small and weakly interacting that they pass through entire planets without stopping. The early universe produced a vast number of neutrinos in the first second of its existence, and many of them are still traveling today. Detecting the cosmic neutrino background, the neutrino equivalent of the microwave background, would provide information about the universe at roughly 1 second old. But neutrino detectors currently cannot see neutrinos cold and slow enough to be from that background. This remains a theoretical goal for future technology. Whether any technology will ever crack the wall of the first 380,000 years remains genuinely unknown. The physics is clear about what would be required. The engineering to achieve it doesn't exist yet. What's confirmed is that Webb operates at the limit of what light can tell us, and is pushing that limit further with every observing season. The early universe it reveals is already stranger than predicted, but the way the public receives that information is shaped by something Webb has no control over. A media environment that turns careful, uncertain science into certain dramatic claims overnight. The cycle runs like clockwork. Webb releases new data, a researcher publishes a paper noting that some galaxies appear more massive than models predicted. A science writer summarizes the paper, adding emphasis on the unexpected nature of the finding. An editor adds a headline that drops the nuance entirely. Social media amplifies the headline without the article. Comments fill with people declaring that science has been wrong all along. The video gets 10 million views. 2 months later, Spectroscopic follow-up revises the galaxy's distance. The dramatic finding was smaller than the photometric estimate suggested. A correction appears. Nobody sees it. This loop is real and has been documented in the context of Webb's early results specifically. The pattern appeared immediately after Webb began science operations. Initial photometric candidates suggested galaxies so massive they seemed to challenge the Big Bang. Researchers expressed cautious interest in public papers. Headlines turned that caution into catastrophe. Then spectroscopy did its job. The viral claim outlives the correction every time. And this creates a specific problem. Repeated exposure to "the Big Bang is broken" headlines, each one left uncorrected in the public memory, builds a perception that established science is fragile, that cosmology is constantly collapsing, that nothing scientists say can be trusted. That perception is the opposite of what the evidence shows. Webb's early galaxy findings are genuinely significant. The Hubble tension is a genuine unsolved problem. These are real scientific issues that deserve serious attention, but their significance is different from what the headlines claim. An unexpected galaxy size is a problem for galaxy formation models, a sub-theory, not a refutation of the Big Bang, a foundational framework. A persistent measurement discrepancy means the standard model is incomplete, not that the universe didn't begin with rapid expansion from an incredibly dense state. The science journalist who gets this right explains the actual stakes clearly and resists the temptation to overstate, is doing harder and more valuable work than the one who writes the simplest possible headline. Science communication that preserves nuance is harder to produce and harder to sell, but it's the version that builds genuine understanding rather than recycled drama. For a viewer who's spent time with this video, the difference is now clear. You know what Webb actually sees and what it can't. You know the difference between a galaxy formation model and the Big Bang framework. You know the Hubble tension is a real problem and what's being done to understand it. You know that revised measurements are a feature of the scientific process. That context turns every future "Webb breaks the Big Bang" headline from a moment of panic into a recognizable pattern. You'll know the questions to ask. How large is the galaxy? Was the redshift confirmed spectroscopically? Which specific model does this challenge? Is the Big Bang itself under question, or just a sub-theory? And when you ask those questions, the actual science is always more interesting than the headline claimed. Because what Webb has genuinely changed about cosmology, setting aside every overclaim and misreport, is already one of the most dramatic stories in the history of science. Set aside every overstatement, ignore every Big Bang broken headline, look only at what the confirmed data shows. Webb has permanently shifted how astronomers think about the early universe. Before Webb, the frontier of direct galaxy observation sat at a redshift of around 10 or 11, reached by Hubble after years of deep field imaging. That meant the earliest confirmed galaxies existed roughly 400 to 500 million years after the Big Bang. The period before that was largely theoretical. Researchers had models of what that era should look like, but the observations to test those models at high precision didn't exist. Webb pushed the confirmed frontier to a redshift of 14.32, corresponding to less than 300 million years after the Big Bang. That's a meaningful extension. It brought the era of cosmic dawn into direct observational reach for the first time. What Webb found in that newly accessible era surprised the field. Early galaxies are forming stars faster than standard models predicted. Some early galaxies are larger and brighter than expected. The chemical enrichment of those galaxies, including the presence of oxygen and dust, happened on a faster timeline than assumed. The details of how the first structures assembled need revision. These are confirmed findings backed by spectroscopic measurements. They're not speculation. They are observations that the field now has to explain. On the Hubble tension, Webb played a specific and important role. By confirming Hubble's Cepheid measurements with its superior infrared vision, Webb eliminated the most popular proposed source of error in the local expansion rate measurement. The crowding correction was real but small. The tension is not caused by a Hubble Space Telescope calibration error. The problem is real. That confirmation matters enormously for cosmology. Webb has also detected active supermassive black holes in the early universe at masses that challenge standard growth models. This is a separate confirmed puzzle that requires explanation alongside the galaxy formation surprises. What has Webb changed? It has confirmed that galaxy formation in the early universe was faster and more efficient than the standard models assumed before launch. It has confirmed that the Hubble tension is a real measurement discrepancy requiring a physics explanation. It has provided the first spectroscopic confirmations of galaxies in the cosmic dawn era. These are revisions and extensions. The framework of the Big Bang remains intact, supported by the cosmic microwave background, the abundance of light elements, and the observed large-scale expansion. But the detailed picture of how structures assembled within that framework is being actively redrawn. Future Webb observations will push even further. The James Webb Space Telescope is expected to operate for over 20 years. Every observing cycle adds new spectroscopic confirmations, new distance records, new data on early black holes and galaxy structures. Each new dataset feeds into the revisions underway. The story of the early universe is being written more accurately than ever before, and one specific number at the center of that story has attracted enormous confusion. In the months after Webb launched, a claim spread online. Webb proved the universe is older than 13.8 billion years. Some versions said 26.7 billion years. Others went even higher. These claims appeared in articles, videos, and social media posts with confident certainty. The actual scientific picture is more careful. The age of the universe, around 13.8 billion years, comes from the cosmic microwave background measurements by Planck combined with the standard model of cosmology. It's derived from the expansion rate, the geometry of space, and the density of matter and energy in the universe. It's one of the most precisely determined numbers in all of science. Webb's observations of early galaxies don't directly change that age estimate. Finding a galaxy that existed 300 million years after the Big Bang doesn't mean the Big Bang happened longer ago than 13.8 billion years. It means the Big Bang happened, and 300 million years later, that galaxy existed. The timeline remains the same. The claim that Webb found evidence for an older universe came largely from a 2023 preprint paper by a researcher who proposed that a very high cosmological constant, one inconsistent with other measurements, could explain early galaxy properties by giving the universe more time. This was a speculative theoretical paper, and it required other parameters of the standard model to take values that conflict with well-established observations. Other cosmologists criticized the proposal on those grounds. The paper was a legitimate contribution to scientific debate. It was not a confirmed finding. The online coverage that turned it into Webb proves the universe is 26 billion years old, stripped away all the uncertainty and speculation. Webb itself, as an instrument, doesn't measure the age of the universe. It measures redshifts and galaxy properties. Interpreting those measurements in terms of cosmic age requires a cosmological model. Different models give different ages. The standard model, which fits the widest range of observations, gives 13.8 billion years. Alternatives that fit some observations but conflict with others give different numbers. Choosing between models requires weighing all the evidence, not just the single most dramatic claim. What Webb has confirmed, galaxies existed less than 300 million years after the Big Bang. That's a younger universe when these objects formed than some models predicted would produce visible galaxies. It means structure assembled faster than expected. It does not mean the universe began more than 13.8 billion years ago. The age of the universe is one of the most robust numbers in cosmology. Webb is refining the story of what happened after the Big Bang began. That story is getting richer, stranger, and more detailed with every observation. And the researchers working through these questions aren't simply defending old ideas, they're actively revising their understanding. What they're reconsidering right now, in research institutions around the world, is more interesting than any headline version. The headlines say the Big Bang is broken. The actual conversations in research groups are more specific and more interesting. Researchers are reconsidering the efficiency of early star formation. The standard models assumed that the first gas clouds converted only a small fraction of their mass into stars before radiation pressure and supernova feedback disrupted the cloud and stopped the process. If early gas clouds were converting a larger fraction into stars before disruption, galaxy growth rates would be higher. Observations of early galaxies by Webb suggest something like this may be happening. Theorists are revising feedback models to allow for higher early efficiencies. Researchers are reconsidering the role of supermassive black holes in early galaxy growth. Standard models treat black hole growth and galaxy growth as parallel processes, each influencing the other through feedback. But the black holes Webb is finding in the very early universe are already so large that some researchers think they may have formed differently, possibly through direct collapse, and then actively triggered star formation in surrounding gas. The direction of influence between black holes and galaxies in the early universe is being re-examined. Researchers are reconsidering whether dust production in early supernovae was more efficient than laboratory measurements suggest. The dust in the record holder galaxy requires a source. Current dust production models from supernovae produce less dust per explosion than the observations seem to require. Either more supernovae occurred than expected, or each supernova produced more dust than current models allow, or some other dust source was active. All three possibilities are being modeled and compared to Webb data. On the Hubble tension, the most active theoretical area involves the possibility that dark energy is evolving over time rather than remaining constant. Results from the dark energy spectroscopic instrument in late 2024 added some evidence that dark energy may be weakening slightly as the universe ages. If confirmed with more data, that would require replacing the cosmological constant with a dynamic dark energy model, a significant revision to the standard cosmological framework. Early dark energy proposals continue to be tested against the full range of cosmological observations. These models reduce the Hubble tension but don't eliminate it, and they create new tensions with large-scale structured data. Researchers are looking for a version of early dark energy that improves the tension without creating new problems elsewhere. Whether the Hubble tension points to missing physics in the dark energy sector, in the matter sector, or to a systematic effect in measurements that hasn't been identified yet remains genuinely unresolved. Multiple research groups are working simultaneously on different explanations, and the field is watching carefully for which approach, if any, fits all the data at once. This is what active science looks like: multiple threads, multiple possible explanations, careful measurement, and patient comparison against evidence. None of it is simple, none of it is settled. All of it is moving forward. And at the center of all of it, gathering data that feeds every one of these debates, sits a cold machine nearly 1 million miles from Earth, staring at the oldest light it can reach. Webb was built to see the first light. After decades of planning, thousands of engineers, a budget measured in billions of dollars, and a launch that had to go perfectly or the whole mission would fail, the telescope unfolded itself in the cold of space and started asking the oldest question in science: where did everything come from? The answers coming back are not clean, they're not simple. Early galaxies are bigger than expected. The expansion of the universe disagrees with itself across two methods of measurement. Black holes appeared too early. Stars enriched the universe with heavy elements faster than models predicted. A dust-filled galaxy tells us about a generation of stars nobody has directly seen. Each discovery reveals a universe more complicated than the version we thought we understood. And that complication is the point. Science doesn't advance when everything fits the model. It advances when something doesn't. Every time an observation disagrees with a prediction, a genuine opportunity opens up. The disagreement is a signal. Something is missing. Something is wrong with an assumption. Something real is happening that the model didn't account for. Webb is generating those signals at a pace no previous telescope could match. Each new spectroscopic confirmation of an early galaxy is a data point that theorists have to explain. Each confirmed Cepheid distance feeds into the Hubble tension debate. Each early black hole adds to the puzzle of rapid growth in the infant universe. The The data is building, and the picture is getting more detailed with every observing cycle. What Webb is really asking, beneath every specific discovery, is this: how well do we actually understand the universe? The answer so far is better than we ever have, and still not well enough. The cosmic microwave background maps told us the universe's infancy in broad strokes. Webb is filling in the details of cosmic childhood, the first billion years when the structures we live in were being built for the first time. Every galaxy Webb confirms, at high redshift, is a direct observation of that construction in progress. Webb will continue operating for an estimated 20 or more years. Every year adds new depth fields, new spectroscopic conformations, new data on early black holes and galaxy formation, and the cosmic distance ladder. The dataset will grow, and the models will be revised repeatedly. Future missions, including potential space-based gravitational wave detectors and next-generation microwave background experiments, could eventually push observations even closer to the Big Bang itself, possibly detecting signals from the era of inflation that no optical or infrared telescope can reach. Whether the Hubble tension will be resolved by a revision of dark energy, by new physics in the early universe, or by a completely unexpected discovery remains one of the most exciting open questions in all of science. The universe is about 13.8 billion years old. It contains hundreds of billions of galaxies. Most of its content is invisible to every instrument we built. The edge of what we can see is a wall of fog from when the universe was less than 1 million years old. And behind that wall is a history we can only guess at. Webb is the sharpest eye humanity has ever turned toward that history. And every time it looks, the universe looks back with something we didn't expect. We built a machine to find the beginning. The beginning turned out to be stranger than we imagined. And we're only getting started.